For many of you who took biology 30 or more years ago, all we had was the world of the atom. But of course, atoms are pretty useful things to know about. Atoms make up compounds. Compounds, some are biological in nature, and eventually up the chain you get to us. However, if you want to understand why the atom works the way it does, you have to go to ever smaller scales. You leave the world of atoms and enter the world of what are called elementary particles. So in lectures 4 and 5, we are going to spend a substantial amount of time talking about the world of elementary particles. I refer to these objects as the denizens of the quantum world, and we will meet the denizens and their properties in some fairly great detail. Now, even after we get to elementary particles, there are going to be some problems left. Because you see, in science, and particularly in this kind of physics, we're trying to find explanations for everything. But in order to have an explanation for everything, you actually have to be able to describe everything. So string theory is an attempt to do that. But remember, we've never actually seen a string. So the only tool we will have to explore string theory will be with mathematics. So we're going to spend a lot of time with mathematics trying to tie together the mathematical properties from the objects or the denizens of the quantum world and put those together and achieve this picture of a broader explanation where we will understand the nature of space and time in a more complete manner. There was this process called the power of 10, which is a convenient way to think about where we were going. And we carried it out 10 times, and we found ourselves in the world of the atom. I have here a typical representation of an atom. We see a blob surrounded by other blobs. But these pictures actually make some sense because, in fact, they are representations of a mathematical entity called the wave function. The mathematics of understanding the world of the atom was essentially constructed in the 1930s through heroic efforts by many, many physicists and leads us to this thing called quantum theory. We will see in subsequent lectures that quantum theory describes a very bizarre aspect of our universe, so bizarre that many, many people have a very difficult time accepting that quantum theory can be true. One of these people was Albert Einstein, who, even to the end of his life, expressed grave doubts that such a bizarre kind of mathematics could be part of our universe. From our perspective today, however, we can defend this point of view in the way that scientists always defend their beliefs. Namely, quantum theory works, and we know it works because, well, for you who are hearing these lectures, most of you walk around with cell phones. Those cell phones work because quantum theory works. In fact, quantum theory, with all of its bizarre aspects, is the best tested piece of science in existence. There's a very famous experiment called the G-2 experiment that has been running now for about 40 years. And what the G-2 experiment does is rigorously test the ideas of quantum theory. We will be coming back to this in our next lecture when I'll talk about quantum theory some more, but this lecture is just devoted to a trip to the quantum world where we're going to meet the inhabitants, or the denizens as I like to refer to them, because we're going to meet many a strange entity in this world of quantum mechanics. When we were talking about the atom, there were these blobs in our illustration, and these blobs represent the electron. But the electron turns out to be very peripatetic. It doesn't like to sit in one place. In fact, a way to think about it is electrons are kind of like bugs that buzz around the atom. Atoms, in fact, are surprisingly empty. You want to know how empty? Well, think about a single blood cell in your body in comparison to your entire being. Very great distance in size. That's about the difference between the size of the atom and the size of the nucleus. The nucleus of the atom is to the atom as a single blood cell is to your body. So atoms are mostly just empty space, incredibly empty space. And yet, we think of them as very solid things because atoms are the building blocks for molecules. Molecules essentially are what you need to get to us because they're our basic building blocks. And yet, atoms are mostly empty. The idea that the atom actually has parts is relatively new. It starts with an electrochemist named George Johnstone Stoney, who lived from 1826 to 1911. In 1874, he was performing some electroplating experiments. You know, electroplating, you take two metals, electrodes, you put them in a solution, you pass a current through them, and you can get molecules from one of the metals to migrate to the other. Electroplating. Stoney was in the laboratory performing such an exercise, and he was watching and measuring the flow of the materials, how fast you build up the rates from one electrode to the other. And it occurred to him that he could understand what was going on if the atom could be broken into pieces, and that one of these pieces had to be much, much smaller than the other piece. Now, this is actually very interesting because this is the first time in history someone had the idea that atoms could be broken apart. In fact, the very concept of the atom is quite old. We can trace the notion of the atom as far back as to 480 BC. Leucippus of Miletus and Democritus of Abdera, who was Leucippus' student, proposed that if you started with ordinary matter and you broke it into smaller and smaller pieces, at some point you would reach an object that could no longer be divided. And this was the atmos, the most fundamental entity in the physical universe. And so for the period between Democritus and Leucippus to Stoney, no one had ever thought of atoms breaking apart, because in fact the very definition of atom was something that could not be broken apart. So Stoney's idea in 1874 is a revolutionary idea, that atoms have parts just like machines have parts. And eventually, after having this dream that the atom could be taken apart, the smaller piece he eventually gave a name to. We know this name very well. It's called the electron. So the electron starts off as a dream to explain something. The Nobel laureate physicist Leon Lederman has stated that, roughly speaking, about a third of the economic activity in the U.S. is in some ways related to manipulating electrons. And that's actually kind of right if you think about it, because, well, we need electrons to make computers work, we need electrons to call our friends, we have electronics in the communication industry. Most of entertainment is somehow related to moving electrons around. So electrons are pretty important things. And yet they start from this one guy's dream in trying to understand the dissociation of electroplating. So that's the beginning of our journey to the small. The world starts in the small for us with atoms and electrons. Now, of course, atoms can be disassociated. We talked about the fact that atoms can be broken apart into electrons, and in the interior of atoms, we find two other entities. Here we have our representation in our animation. We have a set of blue balls. Those are representing the protons. The pink balls are representing the neutrons, and those are the other parts of the atom which were basically discovered around the 1930s. So as we encounter this world of the denizens, we first get to a picture. Well, in fact, coming to a picture of the atom is a story of itself. You see, we didn't know what atoms looked like for a very long time. The first person to accurately give us a picture of the atom is the physicist Chadwick, who tells us that in the interior of the atom is an incredibly massive thing. It turns out to be the proton. Later, we find out there's another object there, which is the neutron. So we come to this picture of the atom through struggle and experiment, because that's the way that science works. But it turns out that's not the end of the story. Around 1969, when I was graduating from high school, a set of experiments were performed at the Stanford Linear Accelerator Facility. SLAC is the acronym. And what was done at SLAC was essentially, well, prosaically we can understand it this way. Suppose I had a shoebox and I wanted to know if there was something inside of the box. What would I do? And I was told I couldn't open it. What would I do? How about shake it? Very natural thing to do. You take it, you shake it, you listen to see if there's something rattling. Then you say, yep, there's something inside there or not. Well, essentially, these experiments at Stanford, the Deep Inelastic Scattering Experiments, DIS is the acronym, essentially did the same thing, not to a shoebox, but to protons. Essentially, protons were shaken very hard to see if anything rattled inside. And the surprising result was, yes, we heard something rattling inside. Now, these things inside, which came as somewhat of a surprise, but also were expected from another point of view, were eventually these objects inside were called quarks, named by the physicist Murray Gell-Mann. So let us, in our visit to the world of the microcosm, and I understand, of course, that for those of you who have taken lectures before, there was a nice course called Particle Physics for the Non-Physicist, a tour of the microcosmos. So you can actually go back and review in much greater detail than I'm going to have time to, because remember, for us, this is just a way stop on the way to string theory. So we're just going someplace. But you can review this strange world in much more detail. I'm going to make a brief run through the world. So let me tell you about some of the things that we know about the world of the microcosm. Well, the first thing is that it's populated rather copiously. In addition to the electron, nature has copies of the electron out there. What are these copies? Well, look at my table here and you'll see the letter E. That stands for electron. That's the thing that Mr. Stoney sort of gave us as his greatest gift to mankind. Nature makes a copy of the electron. It's an object that is 200 times as heavy as the electron, but in all other ways, this object is an electron. It's called a mu particle. And then roughly 10 years ago, we found out that nature produced a second copy of the electron. This object is in all ways an electron, but is 1,700 times as heavy as the electron. It's called the tau particle. Now, in addition to these copies of the electron, which are just more and more massive, there are also particles that constitute a different kind of copy of the electron. These other objects have no charge at all. They're called neutrinos. The neutrinos seem to come as copies of the charged leptons. The electron has a neutral copy called the electron neutrino. The muon has a neutral copy called the muon neutrino. And the tau particle has a neutral copy called the tau neutrino. All neutrinos are incredibly light. In fact, up until quite recently, we scientists were convinced that neutrinos had no mass at all. Through a stunning set of experiments performed principally at a facility in Japan called Super Kamiokande, we've learned that in fact neutrinos have mass. And this is a very important fact because neutrinos are by far the most numerous object in the cosmos. And the fact that even if they have a little mass, if they have mass, if they are so great in number, that means that there's lots of room for neutrinos to carry the mass in the universe. So the fact that they're light is a big deal. It's not a tiny deal at all. In addition to this family of objects, which are called leptons, there are other objects. Let's talk about, before we go to these other objects, let's talk a little bit about properties, however. The electron, the muon, and the tau have charge. All of the neutrinos are neutral. Every single one of these objects behaves like a little spinning ball, but spins at a rate that you can neither speed up nor slow down. We physicists have a special name for this rate. We call it h-bar. And in particular, we say that the electron spins at a rate of 1/2 h-bar. But that's also true of the muon, the tau particle, and the neutrinos. All of them spin at a rate of 1/2 h-bar. Here we have a different picture. It's the other set of denizens in the world of the microcosm. In the interior of protons and neutrons are these smaller bits of matter, the quarks. In a neutron, we say that there are 2 down quarks and an up quark. If you look at our illustration, you'll see that there are these little balls. There's a red-blue ball with the letters D next to them. Those are down quarks. And then there's a yellow ball with the letter U. That's an up quark. So a neutron is, in fact, a composite of 3 objects. In a similar manner, if we look at a proton, we see 2 up quarks and a down quark. So the red ball has a U next to it. That means it's an up quark. The yellow ball has a U next to it. It's an up quark. And the blue ball in the proton has a D next to it, so it's a down quark. So this is how we believe nuclear matter is put together. However, the number of quarks, interestingly enough, also comes in 6. Remember in our leptons, there was the electron and 2 copies, and then all the neutral particles for a total of 6 objects. If you look at this table, you see that there's 6 objects once again. There are the up and down quarks, which made up the interiors of the protons and neutrons. Then there are charmed and strange quarks, and these are their names. And then finally, top and beautiful quarks. So there are 6 quarks, except that that's not right. They're actually 18. Well, let's see. 6 times 3 is 18. But if you look back at our picture of the proton, I assigned a color to each quark, and they were exactly 3 colors. So quarks come in this different set of varieties that we call flavors. As you go down this table, we say quarks change their flavor. But each flavor comes in 3 colors for a total of 18. So these are some of the major denizens in the world of the microcosm, the quarks and the leptons. Now these objects have numbers of properties, and one of the most interesting we touched on in a previous lecture, the discovery by the physicist Dirac. Paul Dirac set out to do one thing, but because of the power of mathematics actually did more than he expected to do. He wanted to describe electrons. He wrote an equation for this purpose, but he wound up describing electrons and their antiparticles, the so-called positron. You'll remember perhaps from that lecture that I said that antimatter is kind of a mirror copy of ordinary particles, with the property that if you take an antiparticle and put it at the same location as a particle, you get nothing but energy out. They precisely destroy each other, obeying Einstein's famous equation, E equals mc squared. So for every up quark that I showed you on that table, there's an anti-up quark. For every down quark on that table, there's an anti-down quark. For every charm quark on the table, there's an anti-charm quark. For every top quark on that table, there's an anti-top quark. For every strange quark on that table, there's an anti-strange quark. And for every beautiful quark on that table, well, what is anti-beauty? It's an anti-beautiful quark. So antimatter is real. It's not just science fiction. Of course, science fiction writers have made great use of the notion of antimatter. Starships are driven across galaxies with engines that run on antimatter. I talked about the fact that quarks spin, and it turns out that quarks spin like electrons spin, both at the rate of h bar. They can spin clockwise at a rate of h bar or counterclockwise at a rate of h bar. And so spin turns out to be an important attribute of the world of the microcosm. But it even plays a more fundamental role that we're going to get to in string theory, so I want to pay some attention to this. If we look at particles that have spin, then all of the ones that I've told you about so far share a common property. They spin at the same rate. This property of spinning at the same rate has a very interesting consequence. You're sitting comfortably in your chairs. You're not passing through the chairs, and you probably don't think that's very remarkable. But from the point of view of physics, it actually is a remarkable fact. So physicists like to ask questions like, well, how can you sit in chairs? Well, one reason that you can sit comfortably in chairs is that the chair supports you. That's kind of obvious. But why does the chair support you? The answer turns out to be electricity. The electrons in your body basically are repelled by the electrons in the chair, and that's the force that supports you. In fact, most of the forces that keep me from pushing one hand through the other are in fact electrical in nature. Most of the things that we see in the world around us are contact forces, and their underlying cause is electrical. Now, suppose I could turn off all electrical charges. Remember, for physicists, we look at the world in terms of mathematics. So it's a set of equations. So I get the chance to change the equations however I feel. So let's assume that I can turn the charge off in my equations. What happens then? Well, interestingly enough, you still would not, well, you would dissipate for other reasons, but let's assume that I keep you together for that purpose. It turns out the chair would still support you, interestingly enough. Not because of electrical forces, but because objects that spin at the rate of the electron have the property that no two of them can occupy the same place at the same time. So even if you turn off the electrical charges, there's still a residual kind of repulsion. It's called the exchange force. Now this exchange force is incredibly important because the exchange force is and this fact that no two fermions can, that's their formal name, fermions, we call these things fermions. No two fermions can occupy the same place at the same time, or more precisely, have all the same quantum numbers. That's the way we physicists like to phrase this. Well, when I look at people, I say, but wait a minute, you're not a soup of quarks and leptons. You're much more interesting to look at. Why is that? And the reason turns out to be because in the world of the microcosm, not only are the denizens we've met there, the quarks and the leptons, there are other objects that hold these previous entities in fixed locations, in fixed configurations. Now, these other things are called forces. So let's visit the forces for a moment, at least in the world of the microcosm, and see sort of what is there. Well, if we go to consider the forces, there's one obvious one from our experience. That's the force of gravity. It is responsible for you sitting in your chair. It is responsible for galactic formation, planetary motion. We've recently started to use the gravitational force to detect planets around stars. And of course, there's a famous story of Sir Isaac Newton and the falling apple. And then there are these mysterious things called black holes that we will be visiting yet again in the future, but they're part of the equations of gravity as given to us by Albert Einstein. There's another force in nature called the weak interaction. I was born in 1950, so when I try to talk about the weak interaction, I try to relate it to my experiences as a child. When I was growing up, there were lots of horror movies, and there were these monsters in the horror movies, and they almost invariably glowed. They typically would have a glow associated with them because they were some kind of radioactive mutant. Well, all of that's science fiction, and that's Hollywood, except for the fact that the glow is not. Naturally, radioactive materials do glow. And so there's an energy that's responsible for that. That's the weak interaction, principally through a process we physicists call beta decay. There's the electromagnetic force. Well, gee, we know about that because all of our high technology is essentially built on the fact that we know how to manipulate electrons. We also can explain things like static electricity and lightning, compass needles, light bulbs, computers, all of this because we understand electromagnetic force. And then finally, there's another form of nuclear energy, the strong nuclear force. This is a different form of nuclear energy. This is the form of nuclear energy from which stars derive their energy for light, producing light and heat, which of course, for us on a planet like this is very important. Without our star, we wouldn't be here. So there are four forces in nature: gravity, the electromagnetic force, the weak nuclear force, and the strong nuclear force. And those are the reasons why creatures like us can exist, because our leptons and quarks are held into these nice shapes. Interestingly enough, I talked to you in an earlier lecture about time delays. And in particular, we talked about time delays connected to gravity and with respect to the electromagnetic force. And I told you that Maxwell was the first person to build the time delay into physics because he said that when electromagnetic forces are communicated through space, there's a message carrier. And this message carrier is the photon, the particle of light. Einstein later does the same thing for gravity, where he introduces a message carrier. This message carrier is called the graviton, or the metric. It's another name for this same object. Well, the other forces also have message carriers, because we've named two of them, but we still haven't talked about the two forms of nuclear energy. The weak nuclear force actually has three message carriers. They go by very bizarre names like intermediate vector bosons, Z0, W plus, and W minus. They're very massive objects. And because they're very massive, the weak nuclear force can only extend over a very short range. On the other hand, the strong nuclear force, the energy source for stars, has 8 message carriers. And these things are called gluons. They're all massless, but they have a very strange property that they have the responsibility, if we look back at our picture of the proton as a bubble with these little bits of matter inside, the gluons are the things that make sure that those bits of matter never get outside of the bubble. They are permanently confined to the interior of nuclear matter. So these are aspects of what we call the microcosm. And as I said, there's been a wonderful lecture given on this in a previous set of lectures, and I would certainly recommend that you go and look at them. I earlier talked about the way forces worked in a previous lecture also. So we're going to borrow this picture because it works just fine in the world of the microcosm. The message carriers really are the objects that carry messages from one bit of matter to another. And it's the picture that we've seen before. Namely, the blobs of light represent electrons, and the wiggly line in the middle is the message carrier. It's the particle of light for the electromagnetic force. But wait a minute, there are three other forces. So do they each have message carriers? The answer is yes, we've reviewed them. And interestingly enough, they work in exactly the same way as this picture. For the gravitational force, instead of a particle of light being the message carrier, the graviton is the message carrier that tells two objects they ought to be attracted to each other, because gravity always attracts. But the structure of the picture is the same, that a message carrier is going, for example, from the Earth to the Moon. For the strong nuclear force, these blobs of light don't represent electrons, they represent quarks. And so the quarks are in the interior of nuclear matter. The message carrier called gluons confine them there by saying you ought to be attracted to each other. And these message carriers are so strong that when you try to separate the quarks, in fact, all that happens is that you produce new forms of nuclear matter. The quarks never get free. And then finally, for the weak nuclear force, the message carriers are the Z0, the W plus, and the W minus. So that's the world of the microcosm at an introduction. We've met essentially the characters that reside there. We've talked about a number of their properties. In our next lecture, we will continue to talk about properties because there are other things that are important for us to know about these objects. And before I end this, I want to talk about some really astounding things about the world of the microcosm. In our world, it's clear that time flows in one way. We all move towards the future. And until someone builds a time machine, which many of us think very unlikely, we won't move towards the past. In the world of the microcosm, this is not true. It turns out that for our denizens, the quarks, the leptons, for the message-carrying particles, they are perfectly capable of traveling forward in time or backward in time. This is a very great surprise. The person who figured this out first was Richard Feynman, because he wrote some equations and he noticed, and they were describing the electron, and he noticed in the equations that the equations were perfectly reasonable if you interpret an electron moving backwards in time, as opposed to an electron that usually moves forward in time. However, when an electron moves backwards in time, it looks like it's antiparticle. So time reversal at the world level of the microcosm is perfectly reasonable. Another reasonable thing in the world of the microcosm is to interchange charge. Remember we talked about the electron and its mirror particle, the anti-electron? Well, then you can imagine doing experiments where you interchange the two. And it turns out the laws of physics of the microcosm allow that to happen. We call that charge conjugation, or C parity. And now finally, you can imagine doing an experiment by looking at a mirror as opposed to the actual device and making measurements and writing down equations of what goes on in the mirror. And then a different person might do the same thing for what's going on in the experiment. You might decide at some point to compare the equations. It turns out that for most of if you turn off the weak nuclear force, the picture of the experiment that you see in the mirror and the data coming from the experiment will be identical. We call this parity reversal. The physics of the microcosm, if you ignore weak nuclear energy, is parity invariant. It says that it looks the same if you look in a mirror versus looking at the experiment. These properties collectively are called CPT. C for charge reversal, P for parity, that's looking in the mirror, and T for time reversal. And now one of the greatest mysteries, which is still a mystery, the physics of the microcosm is such that if you do all three, so imagine looking in a mirror at an experiment running backwards in time where you have replaced all the particles by antiparticles. I mean, that's, you can think about doing that. It turns out that the equations that I've described for that situation are identical for the equations of our world. This is called CPT invariance. And CPT invariance is one of the greatest mysteries of physics because we have no idea why you should be allowed to look at a movie where particles have been replaced by antiparticles and time is running back and see our world. Thank you.